Assalamualaikum. Our group are from room C. We present about the last lab, that is lab 4, about the transmission line, no-load and matching impedance. Okay. Our lecturer name is TF Dr. Zikri Abadi bin Baharudin, and my name is Muhammad ARHAM bin Masjid Azam, LIS 80, BO8 2010 428.
And my name is Mama Akil bin KAMARULZAMAN. My matric number is B0820100318.
My name is Muhammad Hassan bin SHAFIE. My ID number is B0820100494.
For our first topic, we will talk about overhead transmission line. An overhead power line is a structure used in electric power transmission and distribution to transmit electrical energy across large distance, and it consists of one or more uninsulated electrical cable that is commonly multiple of 3 for 3-phase power, suspended by tower or post. Okay, our transmission line condition is F2 condition, that is no load and matching impedance.
First, I will explain about transmission line at no load condition. Divided by two model, which is transmission line model 140 kilometers and transmission line model 3000 kilometer. This is a electric schematic diagram by considering safety condition, labeling the component, and sending and receiving end section. Okay, now we explain about the electrical schematic diagram for transmission line model 150 kilometer no load condition. First, from the three-phase power supply, go to the power quality meter and go to the power switch module 1 and through the transmission line model 150 kilometer and go to the power quality meter 2, read the value for receiving end and go to the resistive load, capacitive load and inductive load. The three of load is in the open circuit condition, which is no load. Then transmission line model 300 kilometer no load condition. From three-phase power supply, go to the power quality meter 1, that is a sending end section reading, and go to the power switch module 1 through the transmission line model 300 kilometer and go to the power quality meter 2, that meter is reading for receiving end section, and go to the resistive load, capacitive load and inductive load. Three of the load is also open circuit, there is no load. The difference between the transmission line model 300 kilometer and 150 kilometer is based on the reading at the capacitor, inductance in the model. Based on the result, KB, the result of line voltage at receiving end little bit different in case 140 km at medium transmission line, but obviously different in the case of 300 km long transmission line. This is cause of two. One, the warranty effect on long transmission line condition. Two, because of voltage regulation. The warranty effect on no-load long transmission line condition. One, the effect is caused by the interaction between the inductance and capacitance of the line. Two, when the power line is operated at no load or low load condition, the voltage at the receiving end can be higher than the input voltage. If the voltage exceeds the rated value of the line, it can result in the dangerous situation and cause stress to the cable and component. And third, warranty effect is well known and should be taken into consideration in the design of a power distribution system in order to avoid unexpected voltage increase that can create failures and dangerous situation. Then, to avoid the warranty effect, we need to limit the maximum length of the electrical transmission line. That is why typical power transmission line don't exceed 600 to 700 km at 50 Hz. Next, by reducing the length of the line in order to minimize the phenomenon, the inductance and capacitance of the line can create a resonant situation due to the intrinsic constructive properties of the line itself. To avoid the warranty effect, the common solution is to install an addition reactor, basically an inductance. This compensates for the transversal capacitance of the line and drastically reduce this phenomena. And lastly, the reality of this issue can become much more complex than the explanation offered above. One must think of any possible loss instead of assume the ideal case of the line with a no-load condition. Number two is voltage regulation. The difference of the sending end voltage and receiving end voltage expressed as a percentage of receiving end voltage is called the regulation. Next, efficient transmission line. Efficiency of a transmission line is defined as a ratio of power delivered at the receiving end to the power sent from the sending end. This show the formula, the percentage regulation. No load receiving end voltage minus full load receiving end voltage. Divide by full load receiving end voltage and multiply with 100%.
Okay, I will continue. Okay, C. Compare the maximum result with the calculated volume then make you summary based on comparative analysis. Okay, first, compensation the measurement result. Okay, more voltage drop and current in second table on 300 km transmission line. Zero lattice power and very less equal to 1 volt in 150 km. After that, relative power requirement is highness in 300 km line than in 100 km, 150 km line. Obviously, that power is high in 300 km line, mean capacity of capacitor is large. Okay, this is formula. Okay, next. Okay. Variety effect reduce. Electrical devices are designed to work at some particular voltage. If the voltage are high at the use, their equipment get damaged. And here, when die burn because of high voltage variety effect on long transmission line at low load or long load increase the device peak power. This voltage can be controlled by patching the sub reactor at the referring peak of the line. Okay. Next, sharp reactor is an inductive current element connected between line and nuclear to compensate the capacitor current for transmission line. When this effect occurs in long transmission line, sharp reactor compensates the capacity VAR of the lines and therefore the voltage is regular within the specified limits. Okay, next.
Yeah, next I will discuss about our topic. Matching condition. Okay, matching condition as to transmission line model that is 150 km and model 300 km. Okay, for matching condition, electrical schematic diagram by considering safety condition, labeling and component, and only at the receiving end section. Okay, this is receiving end section. As you can see, they have a power quality meter, resistive load, capacity load, and inductive load. Okay. Based on data table 3 and table 4, we will discuss the result based on the following. Okay, for our question, what can you suggest the result in the medium transmission line for 150 km and long transmission line that is 300 km? Okay, we suggest that fatigue effect from the result. Fatigue effect observed in the long transmission line is more at the low load, the receiving end voltage is higher. At the higher load, the drop in the voltage at the receiving end is observed more in long transmission line. Voltage regulation is poor in long transmission line compared to the medium one. This phenomenon was discovered by electrical engineer that called Sebastian Ziani differenti. Okay, next. Okay, second question is compare the measurement result in medium transmission line and the long transmission line. Okay, for the medium transmission line, the shunt admittance must be included in calculation and the total admittance is usually modeled. They are pi model as two capacitors of equal values, but for the long transmission line, it is not accurate enough to approximate the shunt admittance by two constant capacitors at either end of the line. It is possible to model a long transmission line as a T model with modified series impedance, that is Z, and the modified shunt admittance, that is Y. The ohmic losses in the transmission is high in long transmission line, so the efficiency is less. As mentioned, the ferritic effect is more dominant in long transmission line. Load increase, the reactive power drawn by the line increase. Rating of shunt capacitor and reactor to be used for the long transmission line will be higher than the medium transmission line. Long transmission line, the line inductors to be decreased by increased GMD of conductor, so the voltage drop in the line, the reactive power drawn by the line decrease at the higher load. Okay. Okay, this is our circuit for T model, pi model, and T model for long transmission line. Okay, next.
Okay, I will continue. Okay. Based on the data recorded in table 5 and table C, describe the result of the result based on following argument. Okay, first question is what is the relationship of the result in table 5 and C corresponding the matching depending issue. Okay. We see here the voltage transfer between the source and the table is maximum when dependent mesh. The other depending meshing is dependent begin in which the load depending is chose to the much longer than the source expanded the maximum voltage transfer after time power. Okay. In an alternating current AC circuit, the latter defined on frequency. So circuit which expanded mesh at one frequency may not depending mesh if the frequency is changed. That's changed. In the case of a complex source depending ZS and load depending ZL. Okay, maximum power transfer into convenience when Zs equals Zl prime. Okay, when Zs represent the characteristic depending of transmission line, maximum representation is of tightness when Zs equal to Zl. Okay. Second question is compare the maximum result in medium transmission line and long transmission line. Okay, first, lattice power. Okay, this by the result, lattice power, long voltage line to line, current, load and line. Medium transmission line is equal to the volume or highness than long transmission line. Meanwhile, lattice power, long transmission line is highness than medium transmission line. Okay. Medium transmission line gross capacitor is uniformly distributed over the interlength of the line, yet reasonable partiality is obtained by consider the capacitor of such a line lump at one or more places. Okay, long transmission line, the line constant consider uniformly distributed over the whole length of the line and rigorous method employed for the solution. Long distance transmission line are also affected by voltage drop, the same as short line, but by using the highness line voltage, the drop is less of a impedance. Okay, assuming that there is a drop of 1 voltage per 1 kilometer, a 100 kilometer transmission line has a voltage drop of 100 watt if this transmission line when carrying to 150 volt. Therefore, the voltage should be 150 volt with a corresponding loss of 40% of available power. Okay. Lastly, conclusion. Okay. In this session, we are able to identify the characteristic parameter of line operation under load during meshing and during seismic. After that, we understand the different connection and theory by no load during meshing and during seismic condition. Next, we learn an overhead power line is a substitution using in electric power transmission and distribution to ceramic electrical energy around lunch distance. In consist of one or more unisolated electrical cable commonly multiple of 3 or 8 phase power suspended by now or 4. At last, we know the different type of transmission line, which line, kilometer, voltage again, kilometer volt, and line parameter considered. Finally, we also learn effects of voltage globally at the end of lightly load. Long transmission line is called relative effect.
Yeah, this is our report. Yeah, our result that we get for table 1, table 2, and the calculation, our constant circuit, schematic diagram, Formula 1. Okay, this is the result that we get for table 3 and table 4. Okay, this is result for table 5 that we measure. And our receiving session, our question that we answer.
Okay.
And this is our conclusion that we get from our session. Okay, that's all
Yeah.
from our group, room 6.
Thank you.
Assalamualaikum.
Okay, thank you.